Okay. My name is John Dean, and my presentation is on the use of an oscillating double droplet system to create a rapid scanning liquid lens. Oops. All right. So a lens exists with any translucent material with a constant radius of curvature and a differing index of refraction between the material and the outside environment. So rays of light, as you can see over here, travel through the lens and focus on a focal point. And the index of refraction of the lens differing from the outside material causes this light to bend. And lenses have one important property, which is the focal length, or the distance between the lens itself and the focal point of parallel rays of light entering the lens. So in a camera system, an object emits diverging rays of light that travel through the lens and bend through the lens to converge back to a focal point onto a camera CCD. And a camera CCD is just a light sensor. It's like a digital version of film that senses light and produces an image on a camera. So light has to, in order for light to be in focus, it has to travel from one point on an object, diverge, and come through the light on one discrete point on the camera CCD. If this camera CCD was moved forwards or backwards, the light would not converge to one point, and this given object would not be in focus on the camera. So in a conventional glass camera system, using a glass lens, only one focal length can be in focus at once. Because if this distance from the object of the camera changes, then it's not focusing on the rays of light will not be focused onto the camera CCD. So it can only focus on one object at once. And in order to change this focal length of the camera, the lens itself has to move relative to the camera CCD. And so a conventional camera takes time to change between one focal length to the next. You can only focus on one object at once. However, this is not the only type of camera. So my research focuses on what's called the double droplet system, or abbreviated DDS. So a DDS exists when a liquid occupies a hole drilled into a substrate material. So you can see a cutaway diagram of one right here. And due to the force of surface tension on the liquid, the droplet has two spherical caps on the top and bottom that produce a constant radius of curvature and therefore a lens. And is held to the substrate material through wetting attractions between the liquid and the substrate. And this type of lens has a unique property and that has the ability to oscillate. So by oscillating, I mean the shifting of volume from an upwards to a downwards position. Now, an oscillating droplet has the top and bottom of an oscillating droplet change their radius of curvature over time. And this change in radius of curvature changes the focal length of the lens itself. So in a camera system, this changes the distance between the camera and what's in focus, much like moving a glass lens in a conventional camera system. However, oscillations of a double droplet system can happen extremely quickly, at upwards of 30 hertz. So this allows for extremely fast scanning of a camera. Now, the objective of my research was to design and build a camera optic system that utilizes a double droplet system lens and focus on and determine and demonstrate the oscillating capability of this optic system. So the first thing that I did for my project was to design and build a liquid lens double droplet system camera tank. So you can see on the left here is a SolidWorks, it's a 3D modeling program that made a design of this tank and the actual produced tank. So the goal of this tank was not actually for camera use, but for just building and viewing double droplet systems. It was made at RPI using a mill. It's made of milled acrylic, and the substrate in this system is just a milled aluminum substrate. So with this liquid lens box, I was able to take these images of double droplet systems. So double droplet systems, the way I make them in the lab is just by injecting fluid through a syringe onto the aluminum substrate. So the top row of these images are double droplet systems consisting of silicon oil surrounded by water. So you can see the 1/4-inch diameter double droplet systems of different volumes. So on the left is low volume, on the right is higher volume. And as you can see, as the volume increases, the volume specifically of the top droplet increases the most. And this is because of the density difference between silicon oil and water. So silicon oil is less dense than water, causing buoyant forces to push the droplet to an upwards position with a higher volume on top. And this makes the lens less stable. And you can see this effect again in a larger double droplet system. This is a 1/2-inch double droplet system, and it was the largest one ever made at RPI. And you can see how the top volume is significantly larger than the bottom volume. So for the liquid lens in my project, I couldn't have this problem. So I chose a different oil. The reason why I used silicon oil to begin with was because they had it around the lab. It's cheap, relatively safe to work with, and it was good to get practice. However, I need something new, so I used the oil 1-methylnaphthalene for two main reasons. One, because 1-methylnaphthalene has a relatively high index error fraction, and again, index error fraction causes light to bend when it enters through the material, so a higher index error fraction produces a more powerful lens for its size. And also, 1-methylnaphthalene has a density relatively close to that of water. Water is about 1 gram per milliliter. This is 1.02. So the effect of the Boyne effect, or the effect of gravity, would be much less on a droplet of 1-methylnaphthalene. So with a droplet of 1-methylnaphthalene, I did some preliminary image casting. So in the picture on the right, you can see an object showing an image on a piece of paper using a double droplet system lens. So the flame, in this case, creates diverging rays of light that enter through the lens and converge down to an image on the piece of paper. And you could see different objects placed in front produce different images, and it was clearly focusing light in the way I wanted. So I tested this with a camera behind the double droplet system, and this is an image of myself from across the room. And the image looks slightly better on a computer than it does on this projector, but still was relatively washed out. It wasn't the best quality. And this original double droplet system tank wasn't really ideal for producing images. As you can see, there's a large amount of distance between the substrate itself and the piece of paper, and even the bottom of the tank, which is the closest place a camera CCD or a paper to cast light onto could be placed. It's still relatively far from the lens itself. It's almost 1.5 inches. That's the dimension of the bottom of the tank. And what this means in a camera system is that when the double droplet system eventually oscillates, its ability to scan focal lengths would be lessened because I have a much smaller range of focal lengths that I could scan. So I designed a new system. You can see an image in the end of the diagram of another double droplet system tank, but this one was not for viewing them, but mainly just to focus light and use it in a camera system. So it incorporated a 1/4 inch diameter double droplet system lens and the camera CCD as close as possible to the lens itself. So the distance separating the lens and the camera CCD was roughly 1/4 inch. It was the thickness of the acrylic that I used when making the tank. So you can see it's made to be as small as possible in just a focused light. And the mirror over here is not for any optical use, but just for myself viewing the droplet while creating this double droplet system. Normally, as you can kind of see in this picture here, I go get like a top view, and I want a side view so I can actually see how large the droplet was when I was making it. So that's just what the mirror is for. It's not for any camera use. So now that I had this system that could effectively focus light and take images, I needed a way to regularly oscillate the lens. So I created this oscillation chamber. So the way this works, you see this in the diagram, there are two magnets that are attracted to each other and sandwich a latex membrane in between them, which hold them together well. So this latex membrane seals off two chambers on either side of the magnets that are then run to tubes on two chambers on either side of the double droplet system lens. So what this does is, because each chamber is sealed from one another, when the magnet is pulled one way on the membrane, the double droplet system lens is displaced and forced to move the other way. So the magnets and the double droplet system are coupled together. So when the magnets move back and forth, so do the droplets. And the magnets move back and forth from these two electromagnetic coils on either side of the magnet. So a voltage, a voltage output from an Arduino with a breakout board power these two coils with some simple code that just create two sinusoidal voltage outputs 180 degrees out of phase from one another, and this causes the oscillation of the magnets. And the voltage waves can be powered at different amplitudes and different frequencies to create different types of oscillation. So I can do low frequency oscillation, high frequency oscillation, and at varying amplitudes. And you can see the actual diagram of the oscillation chamber itself right here. So now that I had both, this is a picture of the final setup that I used. So over here, this is the liquid lens tank itself, and it has an angled mirror over top of it because the liquid lens always faces up, just due to it's easier to seal a tank that's always facing up. I could just put a glass sheet on top of it. If it was on its side, I'd have to design better sealing. So the tank, it always looks upwards, and it looks into a 45-degree angle mirror, so I can look across the room rather than just at a ceiling. This board right here is just a board that powers the camera that's just placed under the lens. Here is the oscillation chamber, and then this is the Arduino and the power board for the coils that drive the system. And on the power board, there are potentiometers to control the frequency and amplitude of the oscillations. So now, yep. So I took many videos. Here are just 5 of the system. Oh, actually working. So this first video, you can see the scanning effect of the double droplet system lens. So you can see different objects coming in and out of focus at different times. So the wrench comes in focus, then the room, and then everything gets blurry. And this is relatively low frequency oscillation, so a normal glass lens could do the same effect, most likely by just moving its glass element relative to the camera's ECD. But the next video shows the same thing, now happening a little bit faster. So you can still see what's going on, but the oscillations are now at higher frequency, and the scanning is happening even faster. The next video shows a different setup. And in the last video, it was still relatively low frequency. You could see what's going on. This is, again, low frequency, looking at a screen window, and then a tree, and then everything is blurry, meaning that an object even further from the camera would be in focus were in the frame. So you can see the oscillation effect. The next video of this one is, again, now even faster. So I'm just doing the same thing as in the last video, but again, I'm showing the higher frequency. And my final video now shows this effect at speeds you can't really see what's going on, but this is the higher frequency oscillation. So the previous videos is happening right now, just at much lower speeds. So this is the same thing, just sped up with higher frequency oscillations. So now back to the PowerPoint. All right, so now you might think, well, what's the use of this lens that just scans really fast? Well, I couldn't do it in my project so far because I was using a relatively cheap camera that just took a steady frame rate video. If you have an oscillating lens at high frequency, let's say 30 hertz, and a camera placed behind the lens that's taking images at 30 frames per second in sync with the lens at the same point in each oscillation cycle, you can produce a steady video with a steady focal length because every video frame is being taken at the same point in the cycle with the same rates of curvature and the same focal length. However, if you change the timing of the video relative to the oscillation of the droplet by just a fraction of a second, you're now looking at a totally new object. So between frames of video, you can change the focal length of the camera from near to something infinitely far away instantaneously within the context of video, because from one frame to the next, you can change this. And in addition, even more importantly, using a camera with higher frame rate, let's say 60 frame per second camera, you could take more than one frame video per cycle of oscillation. So with a 60 frame per second camera and a 30 hertz oscillating double droplet system lens, you can take 2 frames at 2 different points in the oscillation cycle, looking at 2 different objects. And when you compile these videos, you can capture video of two different objects at 2 different focal lengths at the same time with one camera setup. So this has various applications in security cameras or military cameras where 2 objects of interest or even 3 objects of interest might be in view of the camera at once, but at different lengths from each other. So a conventional camera would have to choose one or the other to focus on. This kind of system could focus on multiple objects at the same time. And additionally, a double droplet system oscillating at lower frequency on the scale of 1 to 2 hertz with a conventional camera taking images behind it is scanning through a room at low frequency. And what this can be used for is quick 3D scanning. So the focal length of the double droplet system camera over time can be calculated through its oscillation cycle. And if you know the timing of the videos being captured, what time they're captured relative to the cycle, and you can analyze the images to look at what's in focus, you can now determine the distance between what's in focus and the camera. So you can make a 3D map of the environment faster than a conventional lens could because you can oscillate at a higher frequency. However, there are a lot of improvements I need to make on my current system to be able to do something like this. So the largest improvement that I could make would be the inclusion of a aperture stop. So as you can see in some of the videos earlier, and they're better on a computer than they are on the projector, but they still are relatively low quality compared to standards of normal cameras produced today. And the main reason for that is the lack of an aperture stop. So what an aperture does is it restricts the amount of light entering the camera to only using the middle of the lens. And the middle of the lens is where the least amount of imperfections in the lens, in the curvature of the lens are. As you get farther away from the middle, the lens is more likely to have imperfections that cause blurry video. And also, because these lenses are spherical, and in reality, parabolic lenses actually focus light the best, the middle of the lens is the most ideal because the middle of a sphere, the top cap of a sphere, is closer to a parabola. As you get farther from that middle point, it differs more and more from a parabola. And so an aperture stop restricts the system to only using the middle of the lens. And it's useful for when you're taking videos outside, where in my case, I had to put a filter on, like sunglasses, to restrict the amount of light. Using an aperture stop would restrict the amount of light as well, but much more effectively. and without restricting the amount of light in like an outdoor setting, you produce washed out video because there's too much light for the camera. And the reason why I didn't have an aperture stop in my system was because the aperture stop should be behind the lens itself, but as close to the lens as possible between the lens and the camera CCD. And in my system, that was in the water of the tank. Right outside of the tank was a CCD, so putting an aperture stop there would be ineffective because it's too close to the CCD to work as an aperture stop. In addition, a higher quality CCD could be used. I use a CCD from an old $30 security camera that I ordered in bulk offline. I ordered like 3 of them just because they were cheap and they had a CCD that worked. But a higher quality CCD with higher resolution and customizable image timing could be used to demonstrate the effects I was talking about earlier. And lastly, a spherical and chromatic aberration adjustments could be used. So different wavelengths of light, so different color light, refract differently through a lens. And so different color light actually have different focal lengths. And what that means is in a standard lens without chromatic aberration, you get some color defects in your camera, and certain color light is actually a little bit unfocused. So correcting for this would slightly improve image quality, although it's pretty minute compared to adding an aperture stop. And then another thing I could do is make a smaller system, because at smaller scales, surface tension controls a droplet more than the force of gravity. So there'd be less disturbances in the lens as it moves around or anything while it's capturing video at smaller scales, because surface tension is dominant. So I would like to acknowledge Mr. Jenkins for running this program, Mr. Judd, or for allowing the program to run, Mr. Judd for running the program, Professor Hurst and Chris Tillger. Professor Hurst is the owner of the lab that works in RPI, and Chris was a grad student that helped me out. And lastly, my parents and my sister. That's it. Okay, I was told I shouldn't ask this, but any questions?